Anyhow, so equilibrium is a case, and it's very common, and it's very, especially for architects and building engineers. You have a lot of forces acting, but the resultant force is always zero. Furthermore, you have often a lot of torques acting, and the resultant torque is always zero. As a result, the observed accelerations, both linear and rotational, are zero. Our building, for example, has all kinds of steel structure in it. And there's spans in the ceiling. We recognize there's a tremendous amount of force in this building. And in the spans, there's torque action. And yet this building, much to our relief, does not accelerate. And we would be disturbed if it did, especially differentially. So one of the things that designers do who work on these things is they have to understand the materials to know how strong to build it, what type of building techniques we're going to use to construct it, so truss systems or whatever, so that this building can stand not just 1 more Newton than what would be reasonably in the room. You know, what if we bought an extra textbook? What if we have students from the football team in the room for 1 day? And so on. What if we get 4 feet of heavy wet snow on the roof? These are phenomena that are not that hard to extrapolate. And then we have years of hopefully small amounts of degradation, oxidization of the steel, water leaks here and there that enhance the oxidization, and whatever else goes on inside the building, okay, depending on how much it affects the different materials that are in the building. Even with steel and so on, if it's not careful, then you can have galvanic reactions, like electrical battery when you put dissimilar metals together. And you have to think these things through. And the idea being that, especially when we put people in a public place, children are required, generally, to come to school and attend and learn what is asked of them. So, because they don't have a lot of control over the environment, it is incumbent, I think, upon the public to ensure that these buildings are safe, to pass all reasonable expectations. And I believe that's a fair comment. The cinder block walls and all of the fire retardant materials and the fire drills and all the rest of it make me think that we have a reasonable expectation that if we are responsible within the building, there shouldn't be a bad day. We don't build our schools and public buildings out of wood that lead to the potential for fires. We all hear the stories in the 1800s of the Great Fire of Toronto or Chicago or New York or whatever, where substantial portions of the city disappeared because it was made out of wood. Now, that was the material of the day. But we have benefited from research, and so these people who build these things have to know this stuff, and that's where material science is very important. And this extends to what we've been talking about in the sense of deflections. When forces are applied, or which cause stresses on materials, you have a deflection. And this often can be very small, but it's also very important, because in effect these materials have incredibly high spring coefficients. Now, you've seen, for example, you're playing with something and whatever it is breaks and things go flying, and that can be dangerous even, and this is because the thing you're playing with was stretched. And if we just take the simplistic approach and suggest that there's a Hooke's law type stretching going on, when you let it go, it snaps back to its equilibrium point at lightning speed. And depending on what it's connected to or whatever, and or just even there's a propulsive effect. If it comes back, it'll send it this way. And if that is a rope or string and you're in the way, it can really hurt you. So these are all reasons why we have to be careful with these devices in these situations as best we can, especially, as I said back last year, if the solution or the failure scenario is catastrophic, then it simply is not allowed to happen. So if we're hoisting materials with a steel cable and the cable's rated for 100,000 newtons, depending on the situation, you might not put more than 10 or 15 or 20,000 newtons on that cable, because that cable will degrade and it can shake in the wind. And when that happens, of course, you'll overload it. It's not a straight weight anymore. There's effects there. You have to be careful. And so between the design of it and the responsible operation of it, we should be able to remain safe. And then inspections to make sure that for some reason the device has not degraded. And that's what we do every day. Airplanes, before they fly, one of the pilots has to get out and walk around the airplane and check dozens of sites on the plane. One of the things, just to give you an example, and it's very subtle sometimes. You have an aircraft at the front, near the front you'll see these air data ports. And they look like these little things pointing forward because there's a hole in the tube. It's kind of like sort of a version of a pitot tube. But somewhere on the side of the plane you'll see a disc. So this is in the middle, on the front. This is on the side. One of the things that they can do to measure accurately what's going on is differences in pressure. So you have ram air here, and you have air down the side of the plane here. This is called a static port. Now they're just discs. And so what happens now is you have to make sure these things are not obstructed, not damaged, or whatever. But the static port, according to one of the pilots on the video, he said that we have to watch even for ripples in the paint or in the skin of the plane. If there's been a stressing, if there's a few ripples there, it doesn't look like much, it changes the flow of the air past the static port. And this will give erroneous information in the cockpit. How much erroneous, I don't know. But you can have these things. Air France 447 crashed in the Atlantic Ocean. My understanding is that this froze. And so, in part. And so the data they were getting on the screens it didn't make sense to them. And that's always the danger with fancy equipment, because it's going to give data based on these differences in pressure or whatever. And if that's being mitigated by ice or something, then what you're getting won't make sense. But it's so hard to know what the problem is, because there's not going to be a red light saying ice in the port. You won't know that. You have to look at the failure scenarios I talked earlier. And so that's really informative, I think, and to be aware of these things, first as a designer and then later as an operator. Both groups have to be on their games. So first, if we consider the following. So you could have a book on a table. Our building, so our school. A rotating ceiling fan. Such objects are said to be in equilibrium. And so what we're saying here is the momentum is constant, and the angular momentum is also constant. And we'll say a different constant, just to be clear that they're not the same. Now it could be zero, it doesn't have to be. So if the object is static, now we all know the Earth is going around the Sun, and so the Earth is by no means an inertial frame. But if we take small objects on the surface of the Earth, within the precision of measurement, for most cases, we can assume the Earth is a static, is an inertial frame. So a book on a table, for example, or even our school, which is minuscule compared to the size of the Earth, we're fine. The trouble starts when we start looking astronomically and using the Earth as a platform to measure objects in the solar system. That's when the trouble starts. If the object is static, I'll put here based on Earth for now. Doesn't have to be though, but we say the equilibrium is static. And furthermore, then the momentum, both linear and rotational or angular momentum, is all zero. So the static equilibrium case requires a zero sum, and that's a pretty aggressive constraint. Objects in uniform motion will have the acceleration, the linear acceleration is zero, and the angular acceleration also zero. This then implies that the external forces are zero and the external torques are zero. So even though the thing's moving, it's a consistent motion. It's like the ceiling fan. Or a bicycle wheel rolling down a hill, not down a hill, but on a flat surface. Constant rotation, constant speed, not turning. Okay, then you have a dynamic equilibrium point. That's a situation like that. If a body returns to a state of static equilibrium after being displaced by an external force, it is said to be stable. And we see this with different devices. And you can, lift up the corner of a book and let it go, and it goes right back down to its original location. That's a stable book. But if you have a book that's on an angle or something that's somehow balanced, then if you disturb it, it will do something else. One thing that I suspect is clear to this group, but should be said, is that if the external force is said to be zero, this must be zero along all dimensions relevant for the question. Frame of the question, of the situation. Center of gravity. Now normally, we wouldn't bother with a topic like this because in our day-to-day here on the surface of the Earth, there is, the gravity gradients are incredibly small. And as a consequence, the objects are not distorted adequately by the gravity gradient. And therefore, the center of mass is almost always the center of gravity. It's very, there's only, we have to get off the surface of the Earth to find examples of it. So, the gravitational force acts as if, quote, effectively let's get rid of as if here. Acts effectively as if never hurts to read the notes. Let's try it again. So here effectively acts at a single point called the center of gravity. If the acceleration of gravity is the same, and let's say materially the same, because I guess it never really will be. For all parts of a body, then the center of mass and center of gravity agree in location. And that's why we don't really notice it on Earth's surface. So as such, differences in COM, C, or G are quite rare on Earth's surface. We are in effect creating a difference in a centrifuge. Now obviously the effects of centrifuge aren't gravity based, but the effect of sedimenting, of blood and so forth to separate and differentiate things by spinning them rapidly is in effect what you would get if there was a difference between the two. I'm not going to put that on the board because it's not a gravity effect obviously. However, if we consider astronomical cases, we obtain two things. One is the bodies are reasonably large. And two, the force of gravity is proportional to 1 over r squared. So even if it was linear, though, you could make a case that's still in the middle. But if it's 1 over r squared, there's going to be a displacement here. And so what happens here is, say, the moon, the force of gravity here on the front, and the force of gravity on the rear, moon's radius is in the neighborhood of 3,470 kilometers, plus or minus a few, maybe 35, whatever, doesn't really matter. Depends on the mountain you're measuring. And the distance from the moon to Earth, on average, is somewhere in the neighborhood of 375,000 kilometers, say, plus or minus. So if we say the distance of the moon is around 375,000 kilometers, and these exact values don't have to be exact, it's not important. So we can look at this number here being 3,400 kilometers, and this one being, so we're looking at about 1%, that the diameter of the moon is about 1% of the distance. So our moon, roughly 1% of Earth-Moon distance. Which is, so you can do the gravitational equation, so you'd have something like this. The force of gravity is equal to gmm over r squared, okay, and we can say r1, so the near radius here, okay, so that's a smaller number, minus gmm r2 squared. This will be larger as r1 less than r2. The square makes it more interesting, but the difference in force itself doesn't really matter. But we call those forces tidal forces. Okay? What makes it interesting is something else that happens. So Fg1 minus Fg2 is the tidal force on the moon due to Earth. Now, we say, well, the moon's kind of lacking a bit of water. Of course, we found a bunch of ice, but in general terms, you don't see oceans, although there's Mare, I guess there were lava oceans at one time. But nevertheless, we don't see water on the moon, so the idea of tides on the moon seems kind of dumb. But what we're really saying when we talk about tides in general is this, there's a differential gravity force from one side of it to the other. And that's true on Earth as well. Now, what's interesting is that the orbit of the moon is eccentric. So the near point, well, let's just do it this way. So the apogee, something like 400 to 6,000 kilometers. And the perigee is something like 356,000 kilometers. So when we look at it that way, you're looking at roughly delta R about 50,000 kilometers. And if we look at that as a function of the mean radius, now we're dealing with something in the neighborhood of 50 over 375, cancel a few numbers, about 1/5, well, I guess that's not quite right, 1/7, say, okay? So this is in the neighborhood of 14%. That's a pretty big number. Now what happens is, we'll just take the extreme cases for now. At apogee, the tidal force is the least, because you're further away. So the general denominators in both cases are larger. Okay, you've got r1 squared is farther. Okay, and then you add the radius of the moon, which is a constant. But at perigee, it's a maximum. And so this, the period of the moon is 27.3 days. So you get this constant flexing. Of the moon. And we talk about the tidal effects on Earth, but the tidal effects on the moon are greater because the Earth's more powerful. but you just don't see them. But this actually keeps the moon molten. Now the moon is largely frozen, but there's a center part of it. There's enough heat generated by this, we believe, to keep the moon, the core, still liquid. Now when there's an earthquake on Earth, because of seismic activity, the vibrations and aftershocks and stuff generally are over in 4 or 5 minutes, unless you have a subsequent legitimate motion. But the echoing, if you will, of a given motion is generally over in a few minutes. When we went to the moon in the late 60s, early 70s, what they would do, starting with Apollo 13 and beyond, is the booster rocket that they used to propel the command module and lunar module towards the moon, which was no longer required, but was also on a lunar trajectory now, would be slightly moved so it wouldn't actually collide, which is always nice, and then it would be designed to hit the moon. Now, it would hit the moon before they land, just by the way the celestial mechanics works. But starting with Apollo 12 and beyond, they had a nuclear-powered scientific experiments package, of which included seismometers. And they put them in more than one place. And so you could triangulate. They would know the location of the impact, but what stunned the scientists was that this S4B hit the moon with 21,000 tons worth of TNT effect. The moon rang like a bell. The vibrations lasted for over 3 hours, which means that this is pretty much solid. There's no liquid to damp it out. Honestly, there's no liquid, but there's not much. Okay, so it's kind of neat. So there you get some phenomena, and this ability to determine this tidal effect and this flexing between a para-G and apogee. There's a temperature. Now there's an extreme case of that in the solar system, and that is the moon of Jupiter, Io, that looks like a pizza. And it's just the effect on, of course, on Jupiter is that much bigger. So we'll finish with this on this part. So here's Jupiter, and we've got 1, 2, 3, 4. So we've got Io, Europa, Ganymede, and Callisto. So as you move out, the tidal effects are mitigated, because the thickness of the moon is trivial now compared to the distance. So the further out you get, the less the effect occurs. It also can be the difference of how circular the orbit is. The less eccentric it is, the less effect there will be. But this moon here is the one with the volcanoes on it. And the flexing effect heats it up so much that the volcanic lava that comes out on the surface is often a couple thousand degrees. It's really hot. If we move out to Europa, it looks frozen, but many people think is that it has a subterranean ocean, an ocean down a couple hundred kilometers below the top of the ice that may harbor life. So one of the ideas is to land there with some kind of probe that has the ability to drill through the ice, probably with heat or something. 300 kilometers is a long way, though. I don't know. I will see. And it gets progressively less active as you move out, to the point where Callisto is the most cratered body in the solar system. I mean, nothing happens. If we go to Saturn, with a similar set of circumstances, there's a remarkable moon just outside the rings called Enceladus. Again, we use European verbs, so you don't call it Enceladus, that's what you eat for dinner. So this is and Enceladus is one of the most reflective bodies in the solar system. It has an albedo of 99%. And we didn't know why initially, but when Cassini went there, what's happening is the tidal effect is such on Saturn that's causing ice volcanoes. It's heating enough inside, the pressure comes out, and then it freezes. So it's resurfacing itself, which gives you this incredible reflectivity. So you see these dynamisms that occur not just here on Earth. In the case of our tides, the on the surface. The Pacific Ocean is the best example. The Pacific Ocean at the center, when the moon's in the right place, is pulled out of mean sea level by about 15 meters. The water has surface tension, and that draws the water away from the shore, which is what gives you low tide. As the Earth rotates, and the moon's no longer over that, the water's released. And then you get, and there's a bit of an echo, and that's called high tide, and then it comes back again, there's a cycle. Of course, because of that, if you have bays that funnel, then you're going to get higher tides. So, for example, not only the Bay of Fundy, which everybody's familiar with, but you also have cases in Alaska, where you have staggeringly high tides. And then other places around the world where the tides aren't very high at all. So there's quite a difference, even though it's all caused by the same phenomenon. Okay? Interestingly enough, I'm sure you've heard my Titanic story somewhere along the way. The thinking was, in the winter of 1912, we had a very close approach of the moon. It was right on this. And that creates, and they think that that caused an abnormal amount of icebergs to cleave off of the Greenland ice sheet, such as it existed then. And then, of course, with the Davis Strait bringing that water down into the Atlantic, that may well have pushed ice further south, because as I understand it, Captain Smith turned about 2 degrees of latitude further south than he'd ever encountered ice in 30 years of sailing. So on the surface, I think he probably felt we were fine, but this year it wasn't fine. So it's an interesting thing, but this shows you that cataclysms are often brought upon us by a whole bunch of little tiny things that seem unrelated initially, that once in a while line right up and get you. And you can make an argument that that was true for the Titanic as well. Okay, so that's the first part of this chapter. And now we'll move into indeterminate structures and stress and strain. Any questions about what I said so far? Very well. Now, I don't have to introduce this quite as aggressively because you already know this, but we'll just say it aloud. When a fluid in a closed vessel experiences a force in some area, the entire fluid will experience a change in pressure. So, and if it's not in motion, then that pressure will be the same everywhere. It only changes, you get Bernoulli's effects going on when things start to move, but before that happens, you'll probably have very similar pressures. For rigid objects, and I'll use the word rigid in quotations, chemical bonds easily resist shear forces. So a force to an external force stimuli stimulus, let's say, is localized. So if we have a surface like this and we hit it with a hammer, then you get localized effects. Initially below the hammer, but then to the side you're going to get rippling, and you're going to get that over here somewhere there'll be no, if I strike the table over here, down at the other end there, it couldn't care less. You might get a little bit of vibration, but you're not going to get much. And so this becomes very, very localized. I should maybe want to put in the word very. Now we don't have to strike it, we can just press on it. It doesn't have to be always a kinetic event. So this localization is known as strain or stress, sorry. And the unit that is used is newtons per meter squared. And you're going to say to me, well, that's a Pascal. And it is. But the context is different. That's like saying the same with torque. It's a unit of torque, Newton meters. A Newton meter is a joule. We don't say that torque's measured in joules, because there's a context. Okay? So the unit is Newton per meter squared, and this is not converted to pascals for solids. So like I walk across the stage here, where I put my foot down, is pressing down, and there'll be a certain amount of a localized force, but the rest of the stage couldn't care less. Such stresses cause localized deflections of a material. These are usually minuscule. Microns, for example. So we don't see them, which is why we think the object is a rigid. Now we already know this, of course. We have learned that a change in kinetic energy is equal to the work, which is equal to the integral of FdS. So ds, the integral ds cannot equal 0. There must be deflection. Or the force is infinite. And if no other reason, this is not observed. Now we talked about this last year when we did simple machines. Even hammers can give us enormous mechanical advantages. There is still a deflection of some amount. And the reason children play with them is because they'll bang things because it makes noise. The kids love doing that, right? That's what they're for. So, and this type of analysis is actually quite difficult. And the software to model it is actually some of the more expensive software out there. And I know it's dating myself here, but I remember 20 years ago, at one place I visited, one of my students was working, they had fairly new software to deal with stress and strain analysis of materials after you've modeled the shape of the whatever it is. And it was $50,000 a copy, a user license. And that was 20 years ago. Now, obviously the program has improved, but generally the problem with these types of things, whether it's stress and strain analysis, drag analysis, or whatever, or even modeling galaxies, is no matter what computer you have, you can always make the number n bigger and kill any computer. So it'll depend on the resolution that really matters for what you're trying to do, I suppose, as to, but we're certainly going to be better at it. But this is a very challenging undertaking. Elasticity. An object, I'll rephrase this, and again we'll deal with rigid objects, all rigid objects. Have a component of their strain. So this deflection, I should point out, I guess I didn't introduce that for you, but we'll just do it here. So this deflection is called strain. So those of you in AP Physics may think you're experiencing some stress and some strain. Now you know, and you may well think that you're being deformed. So maybe there's some truth to it all. All rigid objects have a component of their strain where if the external force causing the stress is removed, the object returns to its original shape. Without damage. This region is known as an elastic, is known as elastic. Now, Grandma's China doesn't strike you as being elastic, generally speaking, and I can understand that, but it is not. There's still going to be a small amount of elasticity in its ability to handle deflection, otherwise you wouldn't be able to pick it up. You wouldn't be able to hold the T because there would be any type of additional force would immediately move from the static situation to breakage. And so, but materials with a small elastic region are known as fragile. So it's interesting when we hear words we use every day, we kind of know what fragile means, but then you get these technical definitions. You go, oh yeah, okay, that makes sense. You know? Because you might say, it just breaks easy. And you say to someone, well, but why does it break easy? Well, because it's fragile. And you get this circular reasoning. And it's, you know, and you say, well, but what do you, and they say, well, I don't want to think about that much. And the average person doesn't have to think about that much. They know it's fragile, so they're careful with it. They don't expose it to undue stress. So the job is done. But if it's template design, you care about these things. Because if part of your device is fragile, then you have to take care of it. The space shuttle would be, if it landed in Los Angeles, at Edwards Air Force Base, it has to be flown back on the back of the 747 to Florida where it's launched again. These ferry flights were done generally in either 2 or 3 days, which is fine. It also takes time to put the shuttle on the back of the 747. There's a mounting system. Nevertheless, you can't fly through clouds. You don't fly through rain because these drops at the speed of flight impinge on the surfaces of the orbiter, the leading edges of the wing, the nose, and so forth, and these are very fragile. They can take a lot of heat. And on re-entry, that's really valuable. But you can really make an argument that the orbiter, in many ways, is simply covered in glass. And so, as a consequence, you deal with the same kinds of fragility. And this is what, in the simplest phrase, did in the orbiter Challenger, because that surface was compromised. And we'll get into that later on, but that's what happened. And so, again, your operations, knowing from design, you might say, well, gee, can we not have a thermal protection system that's not fragile? And in the late 70s, the answer probably would have been no. So let's just take a sample here. We'll take a steel bar. Just to give you an example of something a little bit different. It's 1 meter long, and it's 1 centimeter in diameter. Okay? So we will hang a mass from the bar and we'll do it longitudinally, so we've got some kind of mount here. So this is our bar here, and we've got some kind of mass. So we're stretching it, okay? And this mass is about 1,000 kilograms, so like a car. The bar would stretch about 0.05% or what's it, half a millimeter? Yep. So you have this pretty substantial force on it, best part of 10,000 newtons, and on this steel bar, and it stretches half a millimeter. You wouldn't even be able to perceive that. Now, just looking at the balance of forces, and just do this on the back of an envelope here, we take, using Hooke's law, kx, so our x is now in the sense of meters, 0.005, okay? Our force is 10,000, so our k value is going to be something special, right? And that's, in a sense, what happens here. So if this thing fails, okay, the car is going to fall, but this bar could be quite a projectile because it's not that massive, and yet you have this enormous force on it if it comes to that. And that's what makes failures of these types of things under stress very dangerous. So we have to be careful with those things. So you'll see situations where we're testing equipment like this, we'll put it in some kind of containment structure and put a camera and watch it fail inside the box instead of right in front of us where we would be injured. Wrong paper. Let's try this one. If we remove the mass, the bar returns to its normal length. So this is, of course, the elastic part of the behavior. So if we increase the force, so we further increase the force, the rod will break. Around 0.2% strength. Now, we said 0.05 here, so 4 times as much. So if we just assume linearity, about 2 millimeters. And if we assume linearity here, then the force, the external force, would be in the neighborhood of 40 kilonewtons. If the bar, and a steel bar, okay, let's say it weighs 10 kilograms. Probably doesn't, but let's say that. If you put 40,000 newtons acted on its 10 kilogram mass, what's the acceleration? It's pretty impressive, right? So that's what makes these accidents so dangerous. So then acceleration is equal to 40,000 divided by 10, let's say, roughly 400 meters per second squared. This is why failures of items under significant stress are so dangerous. So once again, as a professional, you would have to identify that this is a situation that is hazardous and that appropriate protections are necessary to prevent bad things from happening. So first off, we're obviously going to operate this broad bar. We're not going to operate it in this regime at all, okay? And we would certainly operate at nothing, I would think, nothing less, more than this, and preferably less, depending on the situation. Because, again, over time, things get used a bit, right? Things change a little bit. When an object is stressed to the point where it will no longer return to its original shape, it has passed what is known as its yield strength. And these things are generally found by experiment. It's not something that you can use a calculator to find. So, when an object is exposed to a sufficient stress, that it does not break, or in parentheses fail, it is deformed. It is said to have passed its yield strength. Now, I don't know if we have examples here. You might be in the room, but one of the things that children have known to do over the years is pull a spring too far, and it doesn't go back, right? You push too, this is still okay, but if you pull it too long, too hard, it'll look weird, and the spring will not behave as it used to. That's an example of exceeding the yield strength. The important point here, two things. One is, after experiencing a stress in excess of its yield strength, the materials properties, the sort of like possessive properties, are compromised. And without repair replacement, it is not to be used again. So an example that might apply to your world is if you wipe out with your bicycle, what are you supposed to do with your helmet? What do they tell you to do if you had an accident with your bicycle? What do you do with your bike helmet? That's right, you throw it out. Because when you hit something and it's got a decompression to it, then it is exposed to its yield strength. When that happens, then the bike helmet is no longer able to protect you as it was designed to. And the next time you have an accident, your head will do the yielding, which is not the plan. Okay? So bike helmets, even motorcycle helmets, although they tend to be less effective. And then there's, of course, ultimate strength. So exceeding the ultimate strength causes immediate failure. I expect that it would be catastrophic because you are going to move, perhaps you use an extreme force, but you move immediately from the elastic to the yield portion of this thing. And when it experiences the yield, immediately the thing doesn't have the properties it used to have, so immediately it's going to fail. Boom. Because it doesn't take all that much to kill it. But generally speaking, you've exposed it to a force that's well in excess of the yield strength, so it just goes right on through and goes snap. But there's probably a scenario like my suspicion would be is that you have whatever here, and then when it yields, immediately its properties are, depending on how it is, can decline, and if there's an external force that's significant to produce the yield strength, immediately it fails. And that can, like I said, lead to some pretty dramatic events and recoiling and other things that can happen. So for example, if you have things, two poles, and you have a wire between them and they snaps, those poles boom, and that can lead to other problems depending on the forces and accelerations that are involved. So whatever it is, people at the top of the academic ladder need to figure stuff out and need to enforce policies. So you need to make sure that your operational procedures especially with expensive stuff, don't get you anywhere near, I mean, with duct tape, we don't mind an ultimate failure, we tear the stuff all the time. But where it matters, you have to make sure first we don't get to yield strength based on your procedures. Make sure that happens. And if there's a slip and something does happen, you have to order that the stuff is replaced at whatever cost. It's cost of doing business. Because if you're in an industry, whatever it is, where subsequent failure leads to radiation exposure or crash of an airplane or whatever, that's going to cost you way more than replacing the part. Now, the money people are going to grumble, but you don't get to change the laws of physics just to suit your budget. It doesn't work that way. One of the reasons that there's so many cost overruns is not because there's probably two basic reasons. One is sometimes engineers continually design when maybe they need to stop. But I think the bigger problem is that the selling game. You want the contract, and so you give quasi-unreasonable completion dates and things like that to the project, so you'll get the deal. And when you get the deal, it does take as long as it was going to take anyway, and sometimes it takes longer because you encounter things you didn't expect. Because you're dealing oftentimes with unknowns. When they did the Shepherd subway, I think they found they had chalk or something in the ground, and it was more complicated to drill than they thought. And they were constantly going in and out of the stuff. And this changes how secure the tunnels are. I think the same thing happened when they dug the tunnel across the English Channel. And there's stuff when you haven't done it before, you just don't know. There's a point where you got to just go do it and find the problems as they come. Okay. Now let's look at some of the specific stresses and strains. These are the general cases. First, we'll talk about the types of stresses, and then some of the basic situations. And of course, in many cases, you'll have more than one acting at the same time, which is why you make the big bucks. But just to hear the words so that you begin to understand what we're talking about. So you might hear tensile stress. This is a pulling force. And it's often on a cable. We've got lots of those. Shear stress. This is opposite forces. So this gives you ability to flow. Liquids do not have the ability to resist shear stress, so they flow. Whereas the table you're sitting at is quite able to resist shear stress, and so it sits as a quasi-rigid object. Okay? And then we have hydraulic. Sometimes also known as compressive. So these are all compressive stresses. And this is very important in the construction industry because you're building your foundations and all the rest. Think of what's at the bottom of our school. There's something in the ground that's holding all this up. It was put there in 1972 and it's still there. And hopefully it's not cracking. Okay? Now we end up with some older words here, and there's not a great deal of symbols with these things in comparison to other parts of physics, but we can look at it this way. So generally speaking, we have strain, which you know to be the deflection of material, and of course that would be in character with the type of stress we're encountering. I guess there's also bulk stress, but that's another story. We'll get to that later. Then we have modulus, and we have the stress. A modulus is just a big word for a constant that's been measured. So this is of that material, circumstance, whatever it is. And this is just steel. It could be, let's say it's an I-beam. So an I-beam is different than some other, say a box truss or something like that. So you have to, so in the days before computers, engineers would have books of these things. You know, I-beams with this thickness, I-beams with this much flange on them, I-beams this, I-beams that, I-beams with this kind of steel on them, I-beams with that kind of steel on them. Riveted I-beams, welded I-beams, and so on. And all that has been tested by somebody somewhere. So if you're building something somewhere, you think, okay, well, I need a span. Like in my home, I decided I didn't want a 2-car garage, I wanted a big 1-car garage, single door. So instead of having wood across the lintels, the builder put a steel I-beam. So they have to know the right thickness and size. And a builder's not an engineer, they know what they're doing there, and they look it up and they, okay, we need a beam of this size and circumstance. And so then it was brought there. So this is just a fancy word for it, okay? So for tension, you'd have delta L equals capital E times L. I'm sorry. It doesn't matter, but they got the equation the other way. It'll just be the reciprocal, doesn't make any difference. It's the same logic. So stress equals modulus strain, pardon me. I always say write in pencil. So our stress is force divided by area. Our modulus is this E thing, and then the strain is going to be delta L over L in the case of tension. For tensile and compressive stresses, we call this Young's modulus. And you can look it up. My personal dredging from my memory is this is the same Thomas Young that we met back, who was the Egyptologist and did the light experiment, but I may be wrong because my memory is inversely proportional to my age, but I digress. So, but he was a very accomplished man, so it wouldn't surprise me if my memory is still working on that one. If we take a shear case, and then you have, say, something like this, and then it's being pushed from the side, there will be a deflection, some delta X, we'll call it in this case. So the strain here is delta X over L. So you'll have F over A is equal to big G delta X over L, and this is the shear modulus. Now you'll do some of these calculations, but you do not have to remember any of the values for the strains and stresses, but there's a table in your book that will help you with that. If there's, on the evaluation, if there's any need for that, you'll be given the values, so there's no need to fret about that, at least. Hydraulic stress. Here we have a pressure is equal to B times dV over V. So P is a pressure now because we're dealing with a fluid. And delta V, V is a volume. And and B is known as the bulk modulus. Now, as I introduced hydraulics last year, we had the idea that liquids don't accept much compression, and they don't. Whether it's water or oil, it doesn't make any difference, there's not much going on. I think the example I gave is if you go down to the bottom of a typical ocean basin, which is roughly 4 kilometers down, the pressure at the base is about 400 atmospheres, and yet the density of water only increases by about 3 or 4%. So there is, as we always are going to have, a certain amount of strain, but it is very little. And this is what allows the magic of hydraulic rams to service so well in primarily the construction industry, but in other places as well. Because you can pressurize such a ram to resist whatever, and it works pretty well, providing the ram itself is in good condition. And that's the story of chapter 12.